Hello and welcome to the last lecture in our Introduction to Photonics video series. This is going to be our last lecture and in a sense is a segue to other courses in this online curriculum. We started playing with lasers, and as you acquired certain skills in photonics, you will be exposed to lasers that have a higher power. So the whole issue of laser safety starts playing an important role. In the last lecture, we talked about anatomy of a human eye, and we've seen that power or laser power from the lasers poses a hazard to the safety of the human eye. So this lecture number 8, or the last lecture in this video series, is going to be dedicated to the lasers and the laser safety. So in this lecture, we are going to describe the laser classifications based on certain standards established by authorities. We are going to define a concept called maximum permissible exposure, a concept that plays an important role in laser safety. We are going to talk about 3 general types of laser hazard controls. We'll mention and show a few warning signs that are used to indicate the laser safety hazards. We are also going to address the most frequent causes of laser accidents. And finally, we are going to talk about laser safety precautions that you as photonics technicians should take into account when you're working with lasers. So the need to address this issue has been established already back in the 70s of the last century, when lasers have been invented and started being used. And the first standard that has been established is back in 1969. It's been established at the request of the U.S. Department of Labor and addressed the issue of the laser safety. This original laser safety standard has been updated a few times since present time. For example, in 1973, another standard has been established and directed primarily to users such as operators, technicians, laser safety officers, safety engineers, and research personnel. And then there has been a few more updates in 1980, 1986, 1993. There was a revision back in 2000. So as lasers are evolving, as lasers are being developed, so do the laser safety standards are being evolved to address specific issues that are related to the new developments in the whole area of laser safety. So the primary laser safety standard for the industry is so-called ANSI Z136.1, and then there's also a specific type of laser safety standard for educational institutions, so-called ANSI A136.5. These standards can be obtained by different institutions. Specifically, Laser Institute of America, that's been stationed in Orlando, Florida, can give you access to this type of documents, and also they may be available also online. You can purchase these documents that are having pretty large number of pages that you would have to read, especially if you are to be certified as a laser safety officer or a person who's going to be responsible for the safety in photonics or laser labs. You will have to read through these documents, and you will have to study in detail all the aspects of laser safety. So according to laser safety standards, lasers are classified into a few groups based on the potential hazard that they pose. So we are going to start with the class 1, so-called exempt lasers. This type of lasers, this class of lasers cannot, under normal operating conditions, emit a hazardous level of optical radiation. And the lasers that are included in this category is certain lasers that are part of the laboratory equipment, with all beam paths and reflections that are enclosed. So you may have other lasers like of a higher class, like class 4 or class 3, that can be classified as a class 1 if there's a proper enclosure that has been put around that type of a laser. The next in the list of classifications of lasers is so-called class 2. Here we are talking about low power visible laser devices of about 1 milliwatt. So these types of lasers would not have enough output power to injure a person accidentally, but may injure the eye if stared for a long period of time. So that's another important aspect that has to be mentioned. So it's not just about the power or irradiance of the laser, it's also about the exposure time. So you will see that you have to take into account both the power of the laser and exposure time in order to properly quantify whether a laser is posing any kind of threat or risk for laser safety. So back to class number 2. Class 2 usually is gonna be labeled with a caution sign that has to be put on a device. Types of lasers that would go under the class 2 would be many helium neon lasers, not all of them. And these types of lasers are usually used for alignment procedures and optical experiments. So if you have a higher power type of a laser, you don't want to fool around with that type of a laser during the alignment procedure. So the way how you're aligning a higher class laser is basically having another laser that's part of the same laser enclosure that's visible and that's classified as class 2, which doesn't pose the risk. So you're going to do the whole alignment procedure. You're going to align the beam of the class 2 laser, and then you're going to turn off that laser and then turn on the high power laser of class 3 or class 4. That's going to be the main laser for your experiment. Next class is class 3A. Here we are talking about power levels of 1 milliwatt up to 5 milliwatts. These types of lasers cannot injure a normal person when viewed with the unaided eye, but may cause injury when energy is collected and put into the eye using certain focusing optics such as binoculars, etc. So in this class, most laser pointers will be classified. And in this case, you would want to put a danger or caution sign on the device depending on the irradiance, depending on the amount of power that laser is going to radiate. Next class is class 3B. Here we start getting serious in terms of the laser safety. We're talking about power levels from 5 milliwatt to 500 milliwatt. These lasers can produce eye injury when viewed without eye protection. So if you are experimenting, if you're working with a class 3B and class 4 lasers, you have to wear the laser eye protection at all times. So this class of laser would require a danger label and could have a dangerous specular reflections, meaning not only that this laser poses the safety risk if your eyes are exposed directly to the laser beam, but also if laser beam is directed towards the certain reflecting surface that can reflect the laser beam, especially specular reflections or reflections that are not being scattered or diffused in many directions. So as already mentioned, if you are working with class 3B laser, you have to wear the eye protection at all times. And finally, the highest class is class 4. Here we are talking about lasers that have powers above half a watt or above 500 milliwatts. These types of lasers can injure you if viewed directly or by viewing both the specular or diffuse reflections. So here it's not just the specular, but also diffuse reflections. Danger side has to label this type of a laser, and some of these lasers can also present a fire hazard. And in this case, both eye and skin protection would be required when operating this type of a laser. So as this slide shows, lasers according to laser safety standards are going to be classified in different classes, starting with class 1 and going all the way to class 4, from the lowest possible power levels all the way to the highest possible power levels. You also may come across a few other classification updates recently that we are going to talk more in detail in a high power laser class that's going to be part of this online curriculum. Now that we familiarize ourselves with the different safety classifications of lasers, we also want to talk about what type of safety controls would have to be established in a lab or in a space in which you're going to be operating class 3 and class 4 type of lasers. So the main focus here is on the class 3B and class 4 lasers that operate at the power levels above half a watt. And if you are operating these types of lasers, you definitely have to have a very explicitly defined type of laser safety controls in a lab that would prevent any kind of injuries to your eye and to your skin. there's a few different types of control measures according to the laser safety standards. Control measures can be broken down into three main types. You may establish engineering controls, you may have administrative controls, and finally you may wear personal protective equipment, or popularly known as PPE. So when we are talking about engineering controls, we are talking about certain design features or devices. So we are talking about hardware in this case. So certain design features or devices that are applied to the laser beam or laser environment that would restrict exposure or reduce irradiance. So what kind of controls we're talking about here? We're talking about beam shutters, we're talking about beam attenuators, remote firing and monitoring systems, and also protective housing placed entirely around some laser systems. So very often laser labs would have interlocks, the doors would be carefully controlled. There would have to be some sort of laser sign, laser safety light outside that would be turned on during the operation of the laser. And if someone opens the door during the laser operation, there would have to be some sort of automatic shutdown of the laser. So we are talking about a lot of hardware that would be used to reduce any kind of risk of laser safety, of laser injury during the operation of the laser. Not only are we talking about monitoring systems, we are also talking about certain features such as certain walls, beam shutters. You may have a beam dumps that would be collecting the laser radiation. You may have a beam attenuators that would be reducing the amount of power that's coming out of the laser, etc. So a lot of different types of engineering controls that can be established in the laser lab. Next group is so-called administrative control measures. Here we are talking about certain procedures, we are talking about information rather than devices and mechanical systems. So important administrative controls would be posting warning signs and labels, establishment of SOPs or standard operating procedures, safety training. Very often people who are entering the lab would have to sign in with a specific date and time when they enter the lab, and they also have to sign out when they are leaving the lab. Very often those types of laser safety books or operating books in the labs would also include different measurements or experiments that have been conducted in the laser lab. So a lot of paperwork that we're talking about here. So we talk about administrative control measures that can be established in a laser lab. And finally, the third group of safety controls is so-called PPE, or personal protective equipment. So here we are talking about equipment that is worn by the personnel, such as laser technicians, laser safety officers, and then other people who will be present in a laser lab. So we're talking about protective eyewear, we're talking about the gloves, we're talking about special clothing. So anything that can go on an operator or on a human being that is present in the laser safety, in the laser lab, is what's going to go under the personal protective equipment. This slide shows in a form of a table classifications of different types of safety controls listed in 3 columns. So starting with the column on the left hand side, we have engineering controls. So under engineering controls, we would list protective housing and service panels, interlocks on the protective housing, door interlocks, remote control connectors, beam attenuators, beam shutters, key switch and padlocks, filtered viewing optics and windows, emission delay warning lights, emission indicators, beam enclosures, control beam pads, laser controlled area, beam stops, remote firing and monitoring. So a whole bunch of different engineering controls. We are going to study these engineering controls more in detail in the class that is going to be dedicated to the high power lasers and laser systems. In the column in the middle, you have administrative and procedural controls, establishment of a laser safety officer, standard operating procedures, limitations on use by class, entry limitations for visitors, different types of trainings that the operators would have to undergo, maintenance and service manuals, marking on protective devices, warning signs and labels. So a lot of administrative stuff. And finally, PPE or personal protective equipment. There we would have eyewear. We would have clothing and gloves in the case of a class 4 lasers if there is also a risk to the skin injury. An important concept that has to be introduced when it is about laser safety is a concept of so-called MPE, or maximum permissible exposure. So maximum permissible exposure represents a threshold that you're going to establish for every type and class of a laser that would enable you to quantify whether you are operating in a safe environment or you don't operate in a safe environment. So every laser has a certain output characteristics such as wavelength, output energy and power, size of the irradiated area, and also duration of the exposure. And all these different output characteristics are going to define how much exposure to laser is hazardous, and that exposure is going to be quantified to this so-called maximum permissible exposure. So the maximum permissible exposure is a quantity that gives you the information about the greatest exposure that most individuals can tolerate without sustaining injury. So if you're dealing with a specific type of a laser, you would have to analyze and figure out, based on the wavelength and the power levels and also exposure time, you would have to determine from certain specific tables, you have to determine the MPE for that specific laser. And if you are operating that laser, you want to make sure that the amount of irradiance that goes into your eye is below this threshold, below this so-called maximum permissible exposure. If the amount of power that's coming out of the laser is higher, is above the MPE, then you would have to introduce certain laser safety measures to push the MPE, to push the power of the laser or the power that goes into your eye below this threshold. It turns out that MPE, or maximum permissible exposure, is going to depend on both on incident irradiance level coming out of the laser and also exposure time. In other words, you may have the same level of risk if you are handling low power laser over a longer period of time as you would with a high power laser over a shorter period of time. So you have to take into account both the incident irradiance level of laser and then also exposure time. The MPE is usually expressed in terms of allowable exposure time in seconds for a given irradiance. So the unit that we are going to use is usually watts per centimeter square at a particular wavelength. So when you are calculating the irradiance of a laser that you are going to operate, you would want to figure out the irradiance in terms of this unit, watt per centimeter square, because that's what you're going to be comparing to. You want to make sure that you're comparing apples to apples. In other words, you have to compare two numbers that are represented by the same unit. So let's take a first look at the table that can be used to determine the maximum permissible exposure for a specific type of a laser. So the table is shown here on this slide. You can see in the left-hand column laser type. So for a specific type of a laser, let's say helium neon laser, you can see a specific wavelength that that laser is going to operate, and then in a 4 columns on the right-hand side, you have the maximum permissible exposure for different exposure time in seconds. So you can see that, for example, for helium neon laser, you basically have 3 numbers. You have a number for a quarter second, and then you have a number for 600 seconds or about 10 minutes, and then you also have a number for a much larger exposure time of 3 times 10 to the 4 seconds, or 30,000 seconds. So these 3 numbers that you're seeing here for the helium neon laser represent the maximum permissible exposure for a short period of time, for a medium period of time, and also for a long period of time, that are going to be used as the threshold or as the MPE for this specific type of a laser. Let's now go back to the foundations. Let's talk about the absorption and the so-called Lambert's law. So what we are trying to do here is we are trying to analyze the way how laser safety eyewear operates. So this specific optical window that you are seeing here, a specific thickness, is a representation of a laser safety eyewear. So you can see that on one side we have a laser beam that has an incident irradiance level of E sub 0, and as that laser beam is moving through the thickness of the optical window, which is going to be our laser safety eyewear as already mentioned, there's going to be absorption taking place. So the incident irradiance level is going to be dropping down as the light in the laser beam is going to be absorbed by the optical window. So that what comes over on the other side has a significantly lower irradiance level. So our goal is to reduce the amount incident irradiance level on the left-hand side to something that's acceptable or something that's below maximum permissible exposure. So in order to be able to conduct these types of calculations to figure out what type of laser safety eyewear you would want to use in your laser lab for a specific type of a laser, we need to go back to the foundations. We have to analyze so-called Lambert's law that basically quantifies the amount of transmitted irradiance level at the exit of the optical window compared to the input in the irradiance level. So what you are seeing on the right-hand side in the box is a formula or equation that can be used to do those types of calculations. So let's quickly explain this formula. What you see is the factor on the right-hand side that has two quantities in an exponent. One quantity is a quantity alpha, that so-called absorption coefficient. Absorption coefficient is basically coefficient that determines or quantifies the absorptive properties of a material. So for any type of for different types of materials that this optical window is made out of, you're going to have a different absorption coefficient. And then another factor in an exponent is a factor x, quantity x, that represents the thickness of the absorbing material or thickness of this optical window. So we can see that the output irradiance E sub x, the irradiance that's coming at the exit, that's exiting the optical window, is going to be the function. Is going to be determined by the type of a material that optical window is made out of, thickness of the material, and finally the input power levels or input irradiance in a laser beam that's entering the optical window. All this kind of makes a common sense, right? Is a common sense, because we would expect that the amount of light that's going to be absorbed by this optical window is going to depend on the material properties of the optical window, and then also thickness, because thicker the optical window is, the light has to go through more of a material, which means that it's going to be more absorption, or the output power levels or output irradiance levels will be lower. So once more, the absorption coefficient alpha is a property of the absorbing material, and then also is a function of the wavelength of the light. That's why we have this small lambda in the subscript of this coefficient. In other words, the absorption coefficient is going to change for a specific material based on the wavelength of the light that's passing through that type of a material. So if you're talking about eye filters or that are used in the laser safety goggles, the absorption coefficient of the filter is known, and the filter thickness is also predetermined. So very often we don't have to look at both of these quantities separately. In other words, the coefficient alpha and thickness x would not have to be looked separately, but can be replaced by a single quantity that's so-called optical density, also very popularly known as OD. So every type of laser safety goggles is going to be defined by a specific OD number, or so-called optical density. So if we are using that single quantity, our formula is going to be slightly be updated. As you can see on a right-hand side, we are not going to be using the natural base E, but we're going to be using the base 10 in our factor on the right-hand side. And then also, instead of using two quantities, the coefficient alpha and the thickness x, we're going to be using one single quantity OD that is going to determine the optical properties of the eye filter or laser safety goggles that are going to be used. So the optical density by itself is also a wavelength dependent quantity, for a simple reason of it's being a function of the coefficient alpha. And usually optical density is an important quantity that's going to be labeled on the temple of the goggles or on the filter itself. So any type of laser safety goggles that you're going to be using in a laser lab, you would want to look at the top corner of most of time of those laser safety goggles and identify what would be the optical density for a specific wavelength range. Very often there's going to be multiple wavelength ranges that are going to be covered by those laser safety goggles with different OD numbers. So that's an important property of any pair of laser safety goggles that you would want to look at during your determination of whether those laser safety goggles are proper to be used for a specific type of a laser that you're operating. So here we want to put into perspective what this number OD really means. So usually it's going to be some sort of integer. So we want to kind of really understand physically what the specific OD number means. So on the right-hand side, you have a table. On the left-hand column of this table, you can see different OD numbers starting with 0 on the top and going all the way down to number 7, OD number 7. Now, what for example, OD of 3 really means is if you go to the formula on the right-hand side, you can substitute 3 for the OD for 3. So you're going to have 10 to the negative 3, which is nothing else than 0.001 or 0.1%, which means that the laser safety eyewear that has OD number equal to 3 is going to be passing only 0.1% of the original input irradiance level that's entering that type of laser safety eyewear. So you can kind of put physically into perspective what these different OD numbers mean. So obviously higher the OD is, less power or less irradiance is going to be pushed through the laser safety eyewear. So also if you're using a laser with the higher power levels, you would have to reduce the amount of power that's getting out of the laser safety goggles by using the laser safety goggles that have a higher OD number. So very simple equation that's shown in the box on the right hand side is where you can convert the specific OD number into the percentage of the transmission through that type of a laser safety eyewear. And then finally, this slide here is a graphic representation of how laser safety goggles are operating. So on the left hand side, you have a laser that's emitting certain laser radiation. That's here represented by the incident irradiance level of E sub 0. It turns out that E sub 0 for this specific type of a laser is above the MPE, acceptable MPE level. So you would have to use some sort of laser safety protection. So here we are going to use the laser safety protection that's shown here as this filter that's going to have a certain absorptive properties. So this incident irradiance level that's coming out of the laser is going to be significantly reduced as the laser beam is passing through this filter, so that over on the other side, the irradiance level of that laser beam is pushed below the maximum permissible exposure. So the question is, what would be the absorptive properties of this filter, and also what would be the thickness of the filter? So you would want to select a specific type of a filter or specific type of laser safety protective eyewear with a specific number OD that is going to enable the reduction of the irradiance level from E sub 0 all the way down to below MPE, so that if you are looking into that laser beam with a bare eye, your bare eye is going to be protected by this personal protective equipment in a form of a laser safety eyewear. So the way how you're going to do this calculation is shown down below. So instead of E sub x, which is going to be the output power, you're going to substitute a maximum permissible exposure for this specific type of a laser. And if you do a few derivations, you're going to come up with a value for the optical density, or OD, as a function of the incident irradiance levels from the laser, and then also specific MPE number for that type of a laser. If you do the calculation, you know, come up with a number for the OD that is going to be the minimum number OD that your laser safety goggles should have in order to properly protect your eye against any kind of dangerous or hazardous laser radiation. Here we have a few different types of laser safety signs that are used in laser labs. These are slightly older signs, and you can see there's basically three types: danger, caution, and the notice, based on the amount of laser radiation or class of laser that you're operating. So if you're operating class 3B and class 4 laser product, you're going to be using a danger sign. And very often on these danger signs, you would also have a wavelength of the laser labeled, and then over on the other side, on the right-hand side, you have two other signs. One for the lower level lasers, so that's here shown as a caution. Here we are talking about the laser safety sign for a class 2 laser product, and then finally you have also a notice sign that is going to be used for lower power levels of lasers that do not pose a significant laser safety risk for any kind of injury. Here we have a few laser safety signs that are newer or updated. You can see here that in addition to danger, caution, and notice signs, we also have other symbols that are being used that are explained here. As I already mentioned, these signs would very often carry the wavelength of the laser that they relate to, and then also very often there's colors that are being used to further indicate the potential laser safety hazard that a specific laser can pose in a lab that you're working in. How do we define these three different types of laser safety signs is slightly explained on this slide. So if you talk about caution signs, these signs are used for the class 2 lasers and some class 3A lasers, depending on their irradiance. If we are talking about notice signs, these signs will be used for certain temporarily laser controlled areas while service or repair is being done. And finally, danger signs are the most important ones. They are used for certain class 3E lasers of a higher power levels, as well as for the class 3B and class 4 lasers. So danger size is the most important one that indicates a significant laser safety risk that you're dealing with, and a need for a mandatory type of laser safety protection. These slides present a little bit of statistics related to the laser accidents. So we can see different types of laser accidents and different causes of laser accidents. And we can also see that most laser accidents occur because adequate control measurements are not put in place. And as a general statement, as in all aspects of laboratory, field, classroom, or industrial safety, the best measurements would be positive attitude and a common sense. Here we have a few important safety rules that go under the umbrella of laser safety. Number 1, avoid looking directly into any laser beam or at its reflection. Number 2, remove all unnecessary specular or shiny reflecting surfaces from the work area. Number 3, operate lasers in well-defined areas to which access can be controlled. The area should be posted with appropriate signs to alert persons passing by the area that a potential hazard exists. Number 4, the laser system should be operated only by or under the direct supervision of a person knowledgeable of the hazards and control methods for both beam and non-beam conditions. This individual is usually the laser safety officer, or so-called LSO, who is designated by the administration of the company, hospital, or educational institution. The LSO shall have the authority and the responsibility to effect monitoring and enforce the control of laser hazards and to achieve the knowledgeable control of laser hazards. And finally, number 5, any accidents should be reported immediately to the responsible medical authority. If there is an accidental exposure to the eye, the services of an ophthalmologist should be sought. And then finally, at the end, we also want to mention that there's also some other non-beam related hazards in a laser lab. We are going to mention 4 of them here. The first one is the fire hazards for certain types of lasers, especially class 4, that can cause the fire if not being used in a proper way. Number 2 is the explosion hazard for certain types of lasers, such as high pressure arc lamps, filament lamps, and capacitor banks in laser equipment. The third one is electrical hazard because you are dealing with electrical equipment. And finally, the 4th non-beam hazard is a chemical hazard for a specific type of lasers, such as dye lasers. This concludes the last lecture in our Introduction to Photonics video series, and then also concludes the theoretical part of this course. You have acquired a certain set of skills, at least on a theoretical level, that are important and fundamental to be able to work in a photonics lab as a photonics technician. The next part would be the hands-on experience where you're going to be conducting certain experiments in the lab that would further strengthen your set of skills that you learn here through the theory. At the end of this course, I also would like to bring to your attention 3 other courses that are part of this online curriculum. So if you like this first Introduction to Photonics course and you would like to further expand your knowledge in the area of photonics, there's 3 other courses that are being offered through LASER-TEC and the Indian River State College that are listed on this slide. So the next would be the geometrical optics, and then fiber optics, and finally laser technologies. So these 3 classes you can take them in any order you want. But the prerequisite to take any of the 3 would be the Introduction to Photonics course that you just completed. So let's talk a little bit about each of these 3. First, the geometrical optics. So that's the course, that's a continuation of our Introduction to Photonics class. Here we are focusing on different types of optical components, such as mirrors, lenses, prisms. We are trying to see how we can manipulate the light by using these types of optical components. We are also going to make it real world and as practical as possible. We're going to talk about binoculars, we're going to talk about telescopes, we are going to talk about why the soap bubbles would have those beautiful rainbow colors. We are going to talk about 3D polarizing glasses and many other different types of applications of this type of material. The fiber optics course focuses on the aspect of the optical fiber. In this course, you're going to learn about optical fibers, how they're made out of, and then also how they're being used. You're also going to learn how to install the connector on the optical fiber, how to do the fusion splicing, and then also how to perform different types of measurements, including the tier 1 measurement using OLTS, and also tier 2 using optical time domain reflectometer, or popularly known as OTDR. The practical aspect of this course is also very important, where you're going to have an opportunity to work on industrial equipment, such as different types of measurement tools made by the manufacturers that are used in the actual field of fiber optic technology. And finally, the course titled Laser Technologies is an advanced level course in laser systems. Prerequisite for this course is Introduction to Photonics course that you are finalizing right now. In this course that is labeled Laser Technologies, we are going to be operating on types of lasers that are kind of more advanced, especially class 3B and class 4 lasers. We're going to be performing a whole bunch of experiments using different types of equipment, such as beam profilers, spectrometers, and some other. So it's an advanced level class where you're going to be exposed to different types of lasers, starting with basic helium neon lasers, going over laser diodes, talking about CO2 lasers, fiber lasers, and the YAG lasers, disc lasers, etc. So all in all, advanced level class that's going to give you a very nice set of skills to work in some of the coolest places that are operating these types of lasers. So at this point, I want to once more thank all of you for participating in this course. It was a pleasure spending time with you, and once more, thank you for allowing me to transfer some of the knowledge in the field of photonics to you. This is an extremely important field for us because here we are talking about the technologies of the 21st century, for which we need an educated workforce, and most certainly these types of efforts, such as this online curriculum, is an important step in that direction. So once more, thank you very much, and I hope that I'll see all of you in a practical aspect of this course.